All right. I know you don't believe me, but this one actually is going to be really short. I think I have like 3 slides. 6.3, super easy. Heat transfer and thermal equilibrium, way easier than regular equilibrium. So let's get in here. All right, first thing, a review of temperature. Temperature is a measure of the average kinetic energy of the particles involved in the substance, a part of the particles that make up the substance. Okay? Let's take a look at the red curve or the red shape. Okay, this is a Maxwell-Boltzmann diagram. We have seen these before. It's a graph. The y-axis is like number of particles or percentage of particles of the whole substance, and the x-axis is your speed. Okay, so these are not bar graphs, these are sort of curves, okay, and these sort of give you an idea of the speeds of the particles in different substances. At high temperature, your particles are going to be moving faster on average, okay? So that would be sort of, the average would be kind of like the peak of this graph, okay? You're of course going to have some that are going slower, some that are going to be going faster, and a lot that are going here at this sort of median or mean speed, okay? Kinetic energy, or speed, okay? Which correlates to kinetic energy, okay? So, at high temperatures, your molecules, on average, have higher kinetic energy. At low temperatures, they don't have as much energy, okay? So they have, on average, reduced speeds, okay? Smaller speeds. Okay? So, pretty simple, all right? Now, when you have two systems that are at different temperatures, okay, their particles have different average kinetic energies, okay? When you move those together, say a hot block and a cold block, let's say that these are metals, okay? When you move these together, and we'll say they're solids, all right? The heat from the hot block is going to transfer into the cool block, okay? That's how it works, okay? Transfer of heat always goes from hot to cold. I like to think of it as just like heat trying to spread out, okay? Eventually you're going to reach this state over here where both the blocks are the same temperature. That's called thermal equilibrium, okay? So how does that happen? Well, you know, I watched the little video that AP Classroom put together, and they make it really complicated. I don't think it's really that complicated, all right? These atoms in the hot block are vibrating really fast. It is a solid, okay? So the particles are not able to move past one another. They are locked into their positions, but they are able to sort of vibrate in that position, okay? Metals can actually get really hot and remain solid. I mean, really hot. Some metals don't have melting points until you get like into the thousands of degrees, okay? Some of them melt sooner than that, but many of them have really, really high melting points. So these suckers can get really hot, but the atoms are still locked into place. The atoms are just vibrating, okay, in their positions. Now you take a cold metal, one that is, you know, say room temperature or even colder, you put those together, how does the thermal equilibrium come to be? How does the energy transfer from the hot one to the cold one? Well, basically, so here's the dividing line, okay? Now if I find that dividing line here, this right here is where the action is going to happen, okay? The hot, put that in quotations, okay? The fast moving, okay, or the hot atoms from the hot block, as they vibrate, they are literally going to transfer some of their energy to the cold ones through collisions, okay? Through collisions. And many of you that are in physics right now should know that when objects run into one another, you know, fast-moving things can transfer energy to slow-moving things. You have to conserve that energy through like the conservation of momentum, okay, and that holds true here. But if you've got a really fast-moving particle and a essentially stationary or very slow-moving particle, the fast one can bump into the slow one, and it can transfer some of its energy that way, okay? That's called heat transfer, okay? That's what that's called. It's called heat transfer. And I actually had an entire class in college all about heat transfer. We talked about solids, liquids, gases, you name it, okay? So, yeah. So basically, this is kind of like a chain reaction almost. You can think of it as like, you know, these particles here bump into these and cause those to speed up, which then bump into these and cause those to speed up, which then bump into these and cause these to speed up. As this propagates through the metal or through the cold block, it starts to warm up, okay? And so this heat, eventually, given enough time, depends on the material exactly how much time this takes, but given enough time, you will reach a point at which all of the particles are vibrating on average at the same amount, okay? And that's called thermal equilibrium, okay? That's pretty much what this entire thing is all about, 6.3, okay? Now, that was all qualitative, all right? We didn't look at any numbers or anything. It's pretty simple, though, okay? So I've got a sample FRQ here that is going to go through some numbers for you, okay? So we've got a scenario here. An experiment was designed to study the flow of heat from a hot piece of metal to water. So we're putting this hot piece of metal into this water here. The metal starts at 100 degrees Celsius, the water starts at 25 degrees Celsius, and we're just going to drop this metal into the water. We've got a graph which shows the temperature over time. This looks like something to me that honestly could be on like the ACT. Okay, nice little simple graph. We clearly have the metal, which starts at 100, the water, which starts at 25. This point right here, this time, whatever that is, maybe 45 seconds or something like that, 40 seconds, that is when the metal first comes into contact with the water. I know that because that's when the temperatures start, decreasing and increasing respectively. The metal's cooling down, the water's heating up. That's only happening because they've come into contact with one another. Remember, if I go back to this previous slide, thermal equilibrium is reached through collisions. So the particles have to be able to be in contact with one another in order for that heat transfer to take place. So that's where they come into contact with one another. Here is where we finally reach that thermal equilibrium, okay? So that is the point at which the kinetic energies of the molecules of both the metal and the water have reached the same level, okay? So the particles are all moving at the same, on average, the same speed. They're all, moving at the same, they have the same kinetic energy on average at this point in time. So that's at about, I don't know, maybe 130 seconds, something like that, okay? So if I were to look at this on the FRQ section, I would think about all of that. I would look at that graph and I would try to understand what's going on before I read these questions. Now when I read these questions, it's going to be easy. Okay, part A. What is the change in temperature for the metal? Easy. Metal starts at 100 and it goes to whatever this is. I don't know. What is this? This is 37.5, so maybe 35. Okay. What is the change in temperature? I guess technically we should be doing the final minus the initial. Okay, so this would be 35 minus 100, which would be negative 65, okay, degrees Celsius. That makes sense. The change in temperature, it's negative 65. We do know the metal has decreased, okay? You could also, this is the FRQ section. If you said the metal decreased by 65 degrees, you would get credit for that, okay? Because that word decrease is symbolic of that negative sign, okay? But if you had no English and you just had numbers, you would want to have that negative sign included, okay? What time is thermal equilibrium achieved? We already talked about it. It's right here, right? 130 seconds. Justify your answer. Simple. That's the time at which both substances reach the same temperature. Easy. Okay. Part C. Does the average speed of the metal particles increase or decrease with time? Use particle level reasoning to justify your answer. Does the average speed of the metal particles increase or decrease? Okay. Well, temperature is a measure of the speed of particles. Our temperature has gone down, so the metal particles have experienced a decrease in their average speed over time. Use particle level reasoning. Just what I said. I would say temperature is a measure of the average speed of of particles, or the average kinetic energy of particles. So if the metal is getting cooler, then the particles must be slowing down. I think that's fine. Okay. Okay, that's it. I mean, this, man, if you got this as one of your short FRQs on the AP exam, this would be 4 out of 4, right? I mean, I think you guys probably could have answered this question before even listening to this video. Okay, this would be an easy one. Okay. All right, awesome, very, very good. Next video will be on calorimetry, like I said before, which will be much, much more important and perhaps a little bit more difficult than this one. Thanks for watching.